Right. Yeah. Yeah. You don't really have to worry about assignment 5, right? So I have a microphone here. So if you want to speak up, please grab the microphone. All right. Let me make sure recording is on, and screen share is on. All right. So I guess we can get started on the last discussion section. I'll miss you a lot after today, for sure. All right. So today's meme is a multi-core processor, right? This is a pretty popular one, right? Especially for some of the Android phones, where just like one core is doing all the work, and the other cores are just waiting on the side and cheering for that core. Whereas on the other side, if you have two threads that are very competitive, they're gonna fight for the resource, right? They're gonna fight for instruction fetch, for the ALU, for memory, for everything, right? And we need to find a way to deal with them. All right. So remember, Professor mentioned at the end of last lecture that there's going to be some open-ended free response question in the final, right? So that's the main thing we want to address today, how to deal with these kind of questions, right? I just give you these two. Let me move the video screen away and also the control panel. All right. You must still remember this example, right? This is from the lecture. We have A, B, C, D, 4 different implementations of the same program. And we ask you, give you the choice, right? Which one performs better than the other one, because of what reason? But, what if this is a free response question? How do you even get started? Right? There are many things we covered, right? We covered, the impact of branch, the impact of memory, data dependency, superscalar, pipeline, and a bunch of stuff. There are probably like 20 different items that you need to think about, right? So where do you get started? But based on these two codes, just let's rewind our memory a little bit, right? Which one performs better? D performs better, right? And that is because mainly for what reason?
Data dependencies and branch prediction is much better.
Okay, data dependency and branch prediction. Those are some very good answers. What else?
So I don't know if this counts, I guess, but we're going to have loop unrolling, right? So that's a really big optimization, but I guess arguably that's branch prediction.
Yeah, we can do loop unrolling on the D code, right? Not just loop unrolling, but also constant propagation, because the loop bound is already like a constant number. We got some piecemeal solutions, right? But let's have a look at what are all the things you need to worry about. I'm not 100% sure if this is a comprehensive list or not, but I believe this is quite comprehensive. There are 4 main points, right? You need to consider the algorithm behavior, right? Does it take advantage of temporal and spatial locality? You need to worry about compiler optimization. You need to worry about instruction count. And finally, control data and structural hazards. All right. So my tip is that you should evaluate these factors in order, right? But why do you need to consider them in order, right? Like, for example, why do we need to consider algorithm before we start thinking about compiler optimization? Yeah.
Well, so compiler optimizations depend on your algorithm and its implementation. And so if you implement an algorithm in a certain way, like we saw where you make sure to have constant bounds for your loop so you can unroll them, it's like activates the compiler optimization possibility if your algorithm allows it.
Yeah, exactly, right? If the programmer writes the code in a very nice way, it's going to be very easy for the compiler to optimize. But on the other hand, there are many things that compiler cannot optimize, right? So if there's a program that takes, wrote the code in a better way, use a better algorithm like tiling or blocking algorithm, take advantage of locality, these are the things that compiler can hardly figure out, right? So If the programmer does a good job, then the code is going to be better. But and then why compiler optimization comes before instruction count and these hazard considerations? You volunteer, right? Why do I care about compiler optimization before thinking about dependency and hazard, those kind of implementation stuffs?
Is it because compiler optimization can optimize more than if you optimize instruction count?
Could you repeat that?
Is it because compiler optimization has more effect on speed up or than lowering the instruction count?
Yeah, that's right? So if you look at instruction count and hazards, these are the information that we can analyze based on the assembly code. But the assembly code is produced by the compiler, right? So compiler has a great control over, how many instructions you will have as the end result. It can perform all kinds of optimizations, like constant propagation, loop unrolling, and also like reducing a high strength operation like multiplication to a lower strength operation like shift, right? And these will determine eventually the complexity of your instructions, right? And also instruction count. So CPI and IC, both of them will be affected by compiler optimization. All right. And then eventually we also need to care about instruction count and these hazards, right? So why they matter? Because these are the critical factors in the ET, the execution time equation, right? Execution time depends on instruction count, cycle time, and CPI. And for this kind of questions where we run two programs on the same kind of processor with the same frequency, the only remaining factors are IC and CPI, right? IC, instruction count, CPI depends on how we handle the hazards, right? Or how many hazards remain in the assembly code. So these are all the things we need to worry about. But I know, I have like 10 bullet points, and you probably cannot remember them all for the final. So I have a abbreviated version. You just think about, programmer, compiler, and machine, right? How each deals with the program, right? The programmer can write a better program with better algorithm, better locality. The compiler can do all kinds of optimization, particularly if you have loop unrolling and constant propagation. Those are very effective ways to reduce the number of instructions and also to reduce dependency. And finally, right, depending on the exact architecture or all the features in the machine, do we support out-of-order execution, superscalar? What kind of branch predictors? What kind of branch predictors do you have? These will all affect eventually the kind of CPI, data hazard, structural hazard, control hazard calculation. All right. So to recap, programmer, compiler, and machine. Right. I hope that's simple enough for you to memorize. All right. So let's look back into the original examples between B and D, right? So from these three aspects, what can we say? Well, from the programmer's perspective, I can see that the D program is like processing 4 bits at a time, right? So it's a little bit like processing them in batch. So that seems to be a more efficient algorithm. And also it's doing this kind of pre-computation, right? Instead of doing the computation at runtime, we first do a pre-computation and they save them in a lookup table, right? This kind of pre-computation also reduces eventually the instruction count. What about compiler? We have a for loop with constant bound, so that's very easy to unroll, very easy to propagate the constants. On the other side, we have a while loop depending on the variable, and this variable needs to be evaluated at runtime, right? So actually for the D code, eventually we have a good enough compiler, we don't really have any branch instruction anymore. It can be fully unrolled. For the B code, well, you could do unrolling, but unlikely, right? Compiler is not that powerful to identify the pattern. And finally, right, in terms of machine execution, right, data hazard was a little bit hard to argue, right? Because on the D code, even though you have like fewer operations, you're accessing the memory. So it depends on what kind of cache do you have, right? Do you support pipeline of memory execution? All of those factors will affect performance. In terms of control hazard, the branch prediction is going to be quite accurate on branch B, right? On the B code, right? The pattern is, it's going to be taken, and eventually not taken. If you run that code again and again, it's the very same pattern, right? So the accuracy is not bad. But for the D code, we don't have any branch, so it's even better, right? And finally, structural hazard. not much we can say, right? Depending on how many resources we have, what is the fetch width, what is the memory latency, and all of those hardware parameters. Right? So I think that would be a very strong reasoning to put on your final, right? Think of these three aspects in order, right? The most significant to the more machine-dependent optimizations. And then we have different parallel architectures, simultaneous multi-threading, right? Same processor, or I mean, one core running multiple processes, right? Each process will have its own PC to keep track of the status of execution. Whereas on the other hand, we have CMP. What does it stand for? Oh yeah, chip multiple processor. Thank you. Is it like chip multiprocessor or chip multi-core processor? Probably like multiprocessor. Yeah, okay. Chip multiprocessor, right? But eventually you have two cores, you can run two threads separately, right? But they can still communicate through a lower level cache. All right. So what do you need to remember about these two? SMT avoids data and control hazards, right? Typically, when you run into a data hazard, you need to stall the pipeline, right? But with SMT, you can just start running the other thread, right? It's like taking up the free resources. For control hazard, right, we have this branch prediction, and sometimes the prediction is not accurate, right? What we need to do, well, we'll still run the predicted PC, right? The predicted programming counter, but that could be wrong. So we're saving the result at the buffer, and eventually, when the branch is resolved, we're going to clear the buffer, update all the registers or memory if any. Right? But with SMT, right, instead of speculatively executing a potentially wrong branch, we could just, wait for the branch and run another thread in the meantime, right? Without wasting any resource. So the key, well, eventually everything's related to this ET equation. And ET depends on CPI, CPI depends on the three hazards. All right, on the other hand, it's a lot easier. We just separate the two threads, right? They have different cache. They could probably have different branch predictors. They pretty much run independent of each other unless they need to communicate on some data. Right. Again, right, how do we compare the performance of these two parallel architectures? Control, data, structure. Right. On the control side, well, because here we're not dealing with any specific program, we need to think a little bit more abstractly, right, in terms of the interaction between two threads running on these parallel architectures. For the control, we need to know what kind of branch predictors do we have, right? Like, does it handle local branch history or the global branch history? These will all impact performance. And we didn't really specify what kind of branch predictors come with each architecture, right? So that is really an open question. And also, right, if they're going to share, let's say if these two threads are going to share a branch predictor, we need to know, do they have similar patterns, right? Which means a global predictor could give you a good accuracy, or if they have very distinct patterns, where you definitely want to separate their branch prediction, right? And then move on to data, right? The important thing is, do they talk with each other, right? Do they share any data, right? Like one of them is writing to a memory address and the other one is reading from the same memory address. Well, with SMT, you can do that communication through the cache, right? But with multi-core processor, you have to go through a lower level memory hierarchy. The latency is going to be much higher, right? So the data interaction also determines which one is better. And finally, structural consideration, right? Remember, one of the main motivations for CMP is that by designing smaller cores, you can put a little bit more resource on the chip, right? I think in the lecture example, instead of having like 6 units of, I don't remember what, like whatever resource, right? With 2 separate cores, you have 4 and 4. So a little bit more resources. Does anyone remember what kind of resource is that? No, no, but so 6 versus 4 times 2, this kind of difference, right? And you need to look at the exact resource specification for a particular question, and also ultimately, right? Are they using the resource in a balanced way, right? So let's say we have 2 threads. One of them is using a lot of resource, the other is using very few. Then simultaneous multi-threading is probably better, right? Instead of wasting a lot of resource for one thread, we're gonna encourage the sharing of resource, and most of the resource will be taken by the more demanding thread. If they're more balanced, then probably they're gonna perform similarly. Or actually, if you have more resource in the CMP, it's gonna perform better, right? All of these analyses are for each individual point. Actual question, you probably need to balance which one is more important, right? Whether I need to prioritize control consideration or data consideration or structural consideration. That is the real open question. All right, depends. Ultimately, everything depends. But a good analysis, follows the same kind of rational structure. All right. Again, if you don't want to remember all the bullet points, the main question is, do I want to share or separate the resource for these two processes? And when it comes to analyzing performance, again, control, data, structure, right? Never changes. All right, this is a slide I made during the lecture, so it's a little bit ad hoc. Well, we covered quite a few topics today, right? I think well, it's not necessarily the main ones, but the ones that I'm most impressed is about power analysis and also heterogeneous big little core, right? For power analysis, things don't necessarily scale in the way we want, right? Sometimes power becomes a bottleneck, power density becomes very high. So you need to know roughly how power scales with voltage, the processing node, like the feature size, probably some other factors I don't remember. And also energy equals time energy equals time times power, right? You can think of it as a rectangle. You can make it wider or make it taller, but eventually you need to do the same amount of work. You can spread it over a longer period of time, even though you can reduce the peak power, but you're also spending more on the leakage power, right? The power is the summation of leakage and dynamic power. Leakage power always happens in the background, regardless of your operational mode, what is the workload, but dynamic power depends on, the utilization of the processor, the frequency, and things like that. About heterogeneous and homogeneous processor. Homogeneous just having like one type of core, right? It could be a lot of small cores or a few big cores, whereas heterogeneous processor is like take a mix, right? A few big cores, a few small cores. Hopefully, it takes care of both, resource demanding single-threaded applications, but also multi-threaded applications. And the question eventually we need to consider is that do threads parallel well, right? Can we run, are there enough threads for us to run in parallel? And also, the benefit of performance core depends on if you have any demanding single-threaded application, right? They cannot be broken up into multiple threads. All right. Any questions so far? I guess you probably, eventually you want to have another look at this slide and just keep a note of these, the key points, right? All right. If not, yeah.
Why does efficient core exist? I don't understand why it's there. If the P core is so good.
All right. We cannot fit so many P cores on the same footprint.
So it's just for area reasons?
Yeah, for area reasons.
Oh,
and
okay.
eventually the cost reason. Right. So instead, well, the space for one P core, remember in that picture, can fit about 4 efficiency cores, and you always have the same kind of area budget. Right. And the cost increases exponentially as you have a bigger chip due to all the yield, the defect reasons. Right. So you can't have a very big chip. And nowadays people are breaking up their chips into smaller ones and try to fabricate each die individually and then put them in the same package, right? Instead of having one silicon die containing a lot of cores, they have like multiple dies. Each of them will be individually fabricated and they will be connected using some advanced packaging technology, right? So the general trend is that we are breaking things up into smaller pieces, right, to save cost, to improve efficiency. All right. And then a bit of review about a more technical problem, the Snooping Protocol, right? Anyone remember what problem Snooping Protocol solves? What is the name of the problem?
Coherent miss?
Coherence? Not
Oh, yeah.
consistency? It is coherence,
Okay.
right? Like, when we say the same address in two processes, they mean the same address. They're going to read the same data. That is coherence, right? Coherence is more like a spatial problem, right? Same address means the same thing. Consistency is more like a temporal problem, right? Depending on like the order in which we run the instructions, right? When everything's ready, you still have the flexibility of reordering or like intertwining things in different ways. So coherence, right? What do I have on the next slide? All right. So basically, we assume that we have two processors or maybe two cores. Each of them has its own L1 cache or even L2 cache, right? Some very fast caches. And eventually, they're going to share a lower level cache or memory through a bus. And this bus allows them to communicate, right? To broadcast what is happening on my core. Did I write to a particular block? And also monitor the activity of other cores. Right, we have this what's it called, like observer thread in the C code example, right? You can monitor the traffic on the bus. But the implementation doesn't really matter as long as you know what is the end result of each memory access. All right, and within the cache, instead of having the valid and invalid, the dirty or not, the dirty bit, now we have 2 bits, right? Storing this kind of information, the state of a particular cache block. Invalid, right? Meaning that there's no data that I can use. Exclusive, meaning that I'm the only core or I'm the only processor having this cache block, right? Or shared, which means, right now this cache block is shared between multiple processes, but I do have the correct data, so I can just read from the cache block. I can also write, but that requires some additional modification and broadcasting to other cores. All right, so let's have a simple example, right? These are the two processes, the processors. Each of them is running, its own thread, right? And we have some load, like write to the memory and store, read from memory instructions, right? And they happen in this order, right, from top to bottom. So when we first try to load, any arbitrary address, right? They're all referring to the same address, right? Address X. So when I'm loading X into processor 1, it's the first time I'm seeing it, right? So it's going to be a compulsory miss. And right now, the block sits only on P1, right? So this is exclusive to P1. If I load it again, well, the block is in P1's cache, so it's going to be a hit, right? It remains exclusive in P1. Right? I'm assuming that these two processes are executing these instructions in order and starting from a clean memory state, right? Meaning that nothing is in the memory. So right now, it's just following the regular cache access behavior. First time, compulsory miss. Second time, a hit. And right now, the block is only in P1, so it's exclusive in P1, right? So if I'm trying to load it again from processor 2, well, I know that it's the first time processor 2 sees the block, right? It's not in processor 2's cache, so it's going to be a miss. But at that point, I have the same block in processor 1 and processor 2, so the state will become shared, right? Miss in P2, and we're going to somehow communicate through the bus to update the state of the same block in multiple processes to shared. All right, now it's the complicated part. If I do a store on P2, I have the same block in P1, P2. I'm trying to write the new data to P2. Do you remember what will happen? Well, the processor crash.
I think the block will become exclusive for P2, or yeah, and for P1 it'll be invalid. That's
correct, right? Right? Analyze the end result rather than the process, right? The exact implementation varies a lot, right? This broadcast and monitoring or observing mechanism is very complex, but the end result should be exclusive and invalid. But don't forget, we also have the dirty bits, right? In addition to the state bits, the 2 state bits, we also have 1 additional dirty bits. Right? It's going to be dirty in P2. For the invalid block, it doesn't matter, right? We just set invalid to 1 or set it to the invalid state, right? So next time we look at it from P1, it's not a valid block. All right, and when we have multiple processors, right, we're gonna set the invalid flag for all the other blocks, right? The same block in any other processors. And then if I do another store, right now this block is exclusive to P2. If I store it again, it's gonna be a hit, right? And then again, the block is exclusive in P2. So P2 remains exclusive and dirty. It's gonna be a cache hit, right? Nothing changes on P1. If I do a load, what happened?
Hit? No.
It's in the cache.
Yeah,
right? It's
so
dirty in the cache. It's exclusive. So I can read it.
Yes.
Just fine, right? Read the
Okay.
new data, the updated data from the cache. Right. So it's a hit in P2 and the state doesn't change, right? No change to the data happen. Try to load it again from processor 1. Remember, at this point, processor 1 is invalid. Processor 2 is dirty and exclusive. All right. So I know that the new data is in processor 2. I need to somehow grab that data to processor 1.
So P2 needs to write back to the shared cache.
Yeah, P2 is going to write back to the shared cache, and then it becomes what states?
Shared and not dirty.
Shared and not dirty, exactly. All right. And then now it's shared between the 2 processes and in a clean state. Finally, if I load from P2, it's going to be a hit, right? And nothing happened. Is it hard? We just haven't really practiced on this, right? It's not that hard. All right. So that's about the Snooping Protocol. And now a little bit recap from the lecture. This is a slide that I like a lot, right? The summary slide at the end of the last several lectures. We keep talking about different kinds of parallelism instruction level, right? For one thread, different instructions can be parallelized. So on one core, if we have a superscalar capability, we can fetch multiple instructions at the same time. We can run multiple instructions at the same time. They all come from one thread, right? Dealing with a very simple program, I'm able to get some parallelism by parallelizing the execution, fetch, execution, memory, and everything. Right? And we also have thread level parallelism. So this is when someone has written a pretty good program that can be parallelized. It can be broken into 2 threads. And then in order to run the 2 threads efficiently, I need multiple streams that allow me to bring them into execution. They could be brought into one core through simultaneous multi-threading. They could be brought into, sent to 2 cores or multiple cores using chip multiprocessor. All right. And then finally, we also have data level parallelism. This is what we mentioned quite briefly today. For the GPU or for the machine learning specific accelerator, we can break up the whole data computation into a bunch of small pieces, right? Send them to a bunch of different execution units. And that depends on, for one thing, what kind of data and algorithm we're handling, but also how many independent execution units are supported by the hardware. Right? And also the instructions, some of the ISA support the more parallelized instructions, right? That will also improve efficiency. I think we are moving fast. I just have 2 more slides about some clarifications on assignment 5. Assignment 5 is it's really not all that complex, right? Even though we have a lot of writings, but eventually it's a very simple data flow, data dependency graph drawing, and then scheduling exercise. All right. So in this question, we give you 2 programs, right? And we call them 2 threads, but really there are 2 programs. And to put them on a multi-core processor, you just treat them separately, right? Each of them will go to one processor or one core. And therefore, you just do the regular, you draw the regular data dependency graph, you do the regular schedule, right? Nothing special. They work independently. For the simultaneous multi-processor, simultaneous multi-threading, they're going to run on one processor, right? And whenever something is ready, you can start its execution, right? So again, you would have data dependency graph. You have two separate data dependency graphs, but you're trying to schedule them on one table, right? So there's no data dependency between the two threads, but we want to run them on one processor, right? With one set of time and one set of resource. And then you do schedule, and finally, it has 4 parts, but it's keep asking the same question, right? How many cycles does it take? What is my utilization rate of resource, right? Essentially counting empty spots in the scheduling table, and also counting what is the total number of cycles. All right. Again, if you don't remember what is SMT and CMP still, SMT is shared, CMP is separate. About question 2, right? Question 2 is very similar to the lecture example. Remember, we have like two threads, each with 2 lines of code, right? The order in which we run the instruction will determine the final result. 0001, 1011, different combinations, right? It's the same exercise over here. The difference is that, in the lecture example, out-of-order execution will have an impact because within each thread, there's no dependency, right? So you can freely order the 2 instructions in the same thread. But over here, there's a data dependency, right? The second one always depends on first for each thread. So you cannot really do reordering, right? That actually simplifies the problem a little bit, right? Typically, you need to consider first, for each individual thread, what are all the reordering possibilities? And then taking another combination of these reordering capabilities, how do you interleave them, right? Suppose you have 2 streams of instructions, how do you put them on one process, like one execution path? But in this question, out of ordering doesn't matter, so we're only left with the interleaving part, right? Following the original order, how to interleave them. And finally, we want to evaluate the result assuming cache coherence, right? Meaning that if I'm referring to A from the 2 threads, they're referring to the same value, right? That is what coherence provides us. So sometimes these assumptions come by default, right? It's the same as what we have seen from the last week, like perfect prediction comes by default, registry naming comes by default, but those will have an impact on the result if we have a different assumption. All right, so that's all I have for today. I think we are ahead of the plan, but I think that's a pretty good coverage, right? There's not much we need to talk about other than this, the conceptual picture.
I'm ready for the final.
Yeah.
Oh,
right. For 2B for assignment 5, it asks if you wanted to make the system sequentially consistent, what are the key constraints you need to impose? I guess I was trying to think of how to answer that.
Yeah, I guess when dealing with this kind of this question, we only learned one technique, right? Like, you want to enforce some ordering to the execution, but of course you can specify that, each process, they need to run in this particular order, and the 2 processes, they need to follow a fixed order. That is fine, but that is not efficient. A more efficient approach is to set some like breakpoints, right? Second set of yeah. Try not to spell it out, but that's the only technique we learned to enforce ordering.
Okay.
All right. Any questions from the online guys? All right. Any more questions?
Yeah. How does the compute code with 2 threads on board?
So I say if you have a processor that supports both multi-threading and multi-core, right? How is the scheduling handled? That is done by the operating system.
Yeah, so operating system scheduling, it's like a whole thing. Yeah.
Yeah.
So we can only tell it to run parallel, but we can't tell it to run parallel one.
You might have some control over it. We just finished everything. Right now it's like Q&A. We might have some control over like the exact the eventual scheduling result on the hardware, but I don't really know. Yeah. But as a practical example, when the 13th generation Intel processor just came out, people are running different experiments on the Windows 10, Windows 11, and they get different performance. So it's really, 13th generation is the place where we have the big little cores, and Windows 11 can better support it, right? So you do need to have a matching processor and operating system to maximize the performance. But I don't know from a programmer's perspective how you can force particular thing to happen. People try to do some black box profiling of the code, where they know a little bit about the processor specification and they want to see exactly how things are scheduled. So they design some special codes, to create collisions at certain places and avoid conflicts at others, and that allows them to force a program into a particular place of the hardware processor. So, but I guess that's like a more fun and advanced topic. I think I just read them from I heard them from some YouTube videos. I don't really know technically how things work. All right. If there's no more question, that concludes today's discussion section. And I guess I'll still see you tomorrow. Probably not. Well, hopefully in the future as well.